Thank you, Mr. Chairman. You know what? I have to admit it. I cheated. I cheated on my scientific results for many, many years. No, wait, that's not what you're thinking about. Actually, rather than cheated, I would say omitted. I omitted some data, and that was because I was not able to explain why I got this data. And finally, I can tell you why. A few years ago, I presented a method to reduce the noise in an orthogonal fluxgate in fundamental mode. Just a recap. An orthogonal fluxgate in fundamental mode is a very simple magnetic sensor. You have one or more amorphous wires, which are fed by a DC plus AC current, a current which is large enough to saturate the wire in circumferential direction, and you have a pickup coil. So if this current is large enough to saturate the wire, then the first harmonic of the voltage in the pickup coil will be proportional to the magnetic field in the axial direction. This is a sensor which has very low noise, but I found a method to reduce it. And this method was very simple. You have to increase the circumferential anisotropy of the magnetic wire using Joule annealing. You inject a current in the wire, kind of 370 milliamps, and this current has two roles. The first one is to create a circumferential field, and the second one is to warm up the wire to perform the annealing. And this system works pretty well. For instance, here you can see the spectrum of the noise of a sensor based on a single wire, and you can see that if you anneal the wire, your noise gets about half of the original noise. And this is nice because you can just warm up the wire with the current for 10 minutes, and wow, the noise gets half of the original noise. And this is the part where I did not cheat. This is actually true. In fact, you can see that the longer is the annealing time, the lower is the noise. In this graph, you can see the lowest possible noise that you can achieve using a single wire fluxgate with S-cast wire or with 1 minute, 5 minutes or 10 minutes annealing. As you see, the longer is the annealing, the lower is the noise. Then you might wonder, why don't you anneal it for a longer time? Why don't you anneal it for half an hour, for 1 hour? Well, the longer is the annealing, the lower is the noise, right? Well, this is the part where I cheated. Rather than cheated, I would say omitted. I had some data. I knew what happens for long time annealing. I simply didn't present it in any paper because I was not able to explain it. Finally, I'm able to explain it, and I found a new solution for this problem. As a matter of fact, if you anneal for a longer time, the noise rises back. For instance, if you anneal the wire for 60 minutes, you end up with a noise which is even larger than the noise that you have with S-cast wire. So it really makes no sense to anneal the wire for 60 minutes. Now, this fact that the noise increases when you increase the annealing time over 20 minutes really doesn't make any sense to me. Because when you anneal the wire for a longer time, you simply get larger circumferential anisotropy, which is just fine. Because the larger is the circumferential anisotropy, the lower is the Barkhausen noise. So what's the problem with that? In fact, if you watch this graph, you can see that even for 60 minutes annealing, you have a large circumferential anisotropy. Well, actually here you see it indirectly because you observe the axial BH loop. And you can see that in the axial direction, the wire just gets harder the longer is the annealing time. So yes, even for such a long time, you get large circumferential anisotropy. So what's the problem? Why do I get larger noise for long annealing time? Why is the phenomenon reversed after 20 minutes? A few years ago, we believed this was due to the sensitivity. As a matter of fact, when you anneal the wire for a long time, you decrease the sensitivity. Then yes, you have lower magnetic noise, but if your sensitivity is low, well, that's a problem. You don't observe anymore the noise of the sensor, you see the noise of the electronics. But later on, we developed a special electronic, and thanks to a particular preamplifier at the pickup coil, we managed to achieve quite a respectable sensitivity, even for long-time annealing. For instance, you can see here that after 1 hour annealing, we still get 10 kilovolts per Tesla of the sensitivity before amplification. And this means that the wall noise of the electronic, of the magnetometer, accounts for 0.7 picotesla per Hz at 1 Hz, which is very low, much lower than the noise that we observe. Then it means that the reason is not the sensitivity. Yes, of course, the sensitivity decreases when you anneal the wire, but yet that is not the reason. The reason must be found somewhere else. And then, a couple of years ago, I found this paper. This old paper from Professor Vasquez, which was published in 1986. And this is a very interesting paper because it shows that in similar alloys, he was working with cobalt, iron, silicon, boron alloys, which are basically the same alloys we use for our sensors. It was showing that the magnetostriction increases with annealing. Well, it gets larger, of course, when you warm up the alloy, but it does also permanently increase every time you perform some annealing. And that is very interesting because that could be the reason why, if you anneal your wire for a longer time, you get a larger noise, because we know that the noise depends on the magnetostriction. So, is that the reason why the noise increases? We have only one thing to do, to measure the magnetostriction. And how do you measure the magnetostriction of a microwire? Keep in mind that these wires that we use for our sensors have a diameter of 120 micrometers, something like that. Well, the best way to measure the magnetostriction of a microwire is to use the classical method of the small angle rotation. Just read this paper, it's a classic, it's fantastic, and you can achieve really precise measurement of the magnetostriction of this kind of wires, even if the magnetostriction is very low, like in our case. So we took our wires and we have measured the magnetostriction for different annealing time. As you can see in this graph, we achieve a very low magnetostriction constant, kind of -4 10 to the -8 for S-cast wire. And then this magnetostriction, as described in the paper by Vasquez, increases monotonically as we increase the annealing of the wire. In fact, our wire has a slightly negative magnetostriction when we consider it as cast. But then, annealing the wire, the magnetostriction increases, becomes 0, and then becomes positive, up to becoming from -4 10 to the -8 for a cast wire, up to 1.2 10 to the -7 for 1 hour annealing. And that is the problem, because for long time annealing, well, yes, the circumferential anisotropy increases, but not that fast. On the contrary, the magnetostriction still increases. So where do we find the lowest noise? We have a sweet point about 10 minutes because, as a matter of fact, at 10 minutes you still have the same magnetostriction that you have for a cast wire. It's just opposite sign. Instead of -4 is +4 10 to the -8. But the amplitude itself of the magnetostriction is the same. But you have a larger coercivity in the circumferential direction. And that means that overall your noise will be lower. Then, if you increase the annealing time, what you achieve is just increasing the magnetostriction, which doesn't bring anything good to your sensor. And that starts to make sense, but we have to verify if this theory is correct. We have to understand if really the problem of long time annealing is the magnetostriction of the wire, which increases if you anneal the wire for a long time. And therefore we produce sensor using another wire, a wire produced by the Instituto of Physics of Iași in Romania. And the composition is about the same, but in this case, the magnetostriction is slightly positive for a cast wire. And what's the problem? The problem is that if you start with already positive magnetostriction, well, the magnetostriction by annealing the wire just increases and just gets bigger. And therefore, what do you expect? Well, you expect the noise just to get worse. And that's exactly what happens here. As you increase the annealing time, you don't get any advantage by annealing the wire because the noise always gets bigger. And that's because the magnetostriction just gets bigger. Fine. So probably now we know that the reason why we see the noise increasing for a long time annealing is the magnetostriction. But how can we get an advantage from this information? Now we know what was caused the problem that I was not able to explain in the previous years. I don't need to hide anymore those data. I don't need to hide the increase of the noise for a long time annealing. But how can we use this information to improve our sensor? Well, that's very simple. We can decrease the amount of iron in the composition of the wire. In these wires you have a relative proportion of cobalt and iron of 94% cobalt and 6% iron, which typically gives the lowest magnetostriction for S-cast wires, of course. If we decrease the iron, the composition of the wire will give a slightly negative magnetostriction, the lower is the iron. Of course, if you have more iron, you will have a larger positive magnetostriction. So, I tried to create a wire which has 5.8% of iron instead of 6%. So I expect to see a larger negative magnetostriction. And that's actually what I achieved. When I measured the magnetostriction of these magnetic wires with 5.8% iron instead of 6, I get a larger negative magnetostriction. I get 2 10 to the minus 7 instead of 4 10 to the minus 8. So yes, I get a negative magnetostriction which is larger, which is not good because your noise will be larger. But what happens when I anneal the wire? When I anneal the wire for a longer time, even 1 hour, 50 minutes, well, since I start from a negative magnetostriction, from a larger negative magnetostriction, after 1 hour, I'm almost at zero magnetostriction. So, what to expect from the noise when I use these wires for my sensors? Well, if my theory is correct, I should expect a larger noise when I use the S-cast wire. Larger noise because the magnetostriction for these wires with 5.8% iron instead of 6 is larger. But then, after 1 hour annealing, the magnetostriction is almost zero, so the noise should be lower. It should not rise back as it did with the other wires. And that's actually what happens. As you can see in this graph, the noise for S-cast wires is very large. It's about 60 picotesla per root hertz at 1 hertz, which is very large noise. But then, when I increase the annealing time, the noise just decreases. And it doesn't rise back when I anneal for longer time. In fact, for 1 hour annealing, I go down to 1.5 picotesla per root hertz. And that's the reason why, if you want to use these wires, these cobalt iron silicon boron amorphous wires for your sensors, and you want to anneal them for a long time, well, maybe it's better not to use the classical composition with 94% of cobalt and 6% of iron. If you want to anneal them for a longer time, it's better to use a lower amount of iron, 5.8, 5.7%, and you will see that you will get better results. And of course, thank you for your attention.